The last session, what we discussed, about the intermediate. The first intermediate which we learned was about carbocation. I'm sure you got some idea about what is the stability of the carbocation in general. That includes octet completed carbocation, where the octet is getting completed. Then CPM, cyclopropyl methyl carbocation. So that shows extreme stability due to the huge release in the strain. Then we have aromaticity, showing an aromatic ring forms. Then regular resonance, which includes triphenyl, diphenyl. Then we have 3 degree, 2 degree, 1 degree. One exception is benzyl, which is slightly lesser than 3 degree. Then allyl, 2 degree, 1 degree, and so on. And within the least stable ones, uh, methyl carbocation is very unstable. Vinyl is even less stable than that. Phenyl carbocation is even less stable. Then we have acetylene carbocation, then the bridge carbocation, and finally anti-aromatic carbocation. These are also regarded as least stable forms. We learned that the fate of carbocation is to combine with a nucleophile and convert into a neutral molecule. That is one way. The other thing is a base can come and extract a proton from here that helps in creating a double bond. This is mainly the fate of carbocations. Next, we also learned that carbocation undergoes a particularly uh, movement of the positive charges, which we call it as rearrangement. For example, this positive charge is currently lying on 2 degree carbon, but given a chance, it can move on to this 3 degree carbocation by shifting some group from 3 degree positions. Now in here, if you notice, there is a hydrogen present, right? Now this hydrogen basically is a spherical, electron cloud here. And that can interact with this empty orbital on the second carbon. And this entire electron density, it will break it from the carbon, convert into minus H minus, and that H minus will move here. And as the H minus moves here, the position 1 will now attain a positive charge. Now what happened? Earlier, if you notice the number of alpha hydrogens which are stabilizing by hyperconjugation are 4. And now if you notice the number of alpha hydrogens, how many do we have? Here we have 3, 3 and 2. So total 8. So number of alpha hydrogens have increased. In fact, the stability of carbocation should be in the direction where the number of alpha hydrogens are progressively increasing. Okay. Now, rearrangement of hydrogen, that is hydride, alkyl, phenyl groups is observed to generally attain a 1-2 shift happening. Okay. To attain a 1-2 shift, typically this is what you will notice. Okay. Let me show you one more example here, how the shift takes place. For example, if at all I have a carbocation at this position. Okay. Now, from here, let's say, what is the number of alpha hydrogens? Here we have 2. Now, what if the positive charge, the hydride shifts from here to here? So, if a hydrogen will come at this position, positive charge can shift here. This is called 1-2 hydride shift. And now if you compare the number of alpha hydrogens, we are getting this as 5 because this side we have 3, this side we have 2. So it is progressively increasing, so there is no problem. What if I make one more hydride shift? Okay, so that the carbocation further moves on to this position. Now, if you compare the alpha hydrogens, right, you would notice that the alpha hydrogens being 2 plus 1 here, total 3. So have you noticed this? From 5 it is going towards 3. So is it possible? No. So that means here the rearrangement will stop. So at this position, you will not see any further rearrangement taking place. You might feel the case that, sir, the positive charge can from here, if it goes here, it will become very stable. Agreed, but at every step there should be increasing carbocation stability. Then and only then the possibility of this charge can move. Okay. Now let me put the similar group again. Okay. I want you to write down simultaneously along with me, everybody. Check out. Suppose if at all I have a same logic here, positive charge in this case. The only thing I'm changing right now is I'm holding a double bond on this position. Okay. Now let's see the first case 1,2-HS hydride shift. Is it possible? Answer is yes. Here positive charge can come because you could notice alpha hydrogens from 2, now it has changed to 5. Thereafter, if it changes to this position, onto this position here, number of alpha hydrogens are only 2, because this side is the only position, sorry, this side is the only position where we have alpha hydrogens. Okay, but if you compare here, can it undergo, I mean, is this rearrangement possible? Answer is yes. This time the rearrangement is possible. So here 1,2 hydride shift will take place, even though number of alpha hydrogens are less. Reason being, the minute you shift this positive charge here, you will see the resonance stabilization is developed. So plus resonance is occurring. So once the resonance is established, or once the resonance is observed, then you don't have to worry about how many alpha hydrogens it is generating. That is irrelevant. Okay. In fact, now resonance will show resonating structures also. That means double bond can shift here, positive charge can come here. So these two are resonating structures. This is not a rearrangement. So from this step to this step, right, this is not a rearrangement. It is just resonance movement. We are showing that there is a movement of pi bonds, but that is not rearrangement. So if the question is asked how many rearrangement steps that you had done in this case, so it is 1 and 2. So 2 rearrangement steps have taken. In the earlier case, how many rearrangement steps? Only 1. Everybody, is this clear? How to think about carbocation rearrangement? Now, most importantly, which group to migrate? So far, we are noticing we are only shifting hydrogen. Is it always the case? Well, the first priority is always to hydrogen. But if not, there is no hydrogen present, then you will go for phenyl. A phenyl with having an electron donating group would be easily migrating in comparison to only phenyl or phenyl with an electron withdrawing group. So this is the priority. And only then you will think about 3-degree carbon, 2-degree carbon, 1-degree and methyl. Okay, let me show you in this case here. So you can see this is a methyl, isopropyl and ethyl. So case is simple, isopropyl is 2-degree. So that is the 2-degree part which should shift here. So that's why isopropyl has been shifted. So this is the correct shifting of the positive charge. Now in the next case, if you notice, it's pretty clear that between phenyl, methyl and hydrogen, it is the hydrogen which has to shift. So if hydrogen shifts, what will happen? We will get phenyl with carbocation, methyl will be here and we will get CH3. And now we have 2 methyls and 1 phenyl. So phenyl will be shifting. So we'll get methyl, carbon, methyl, CH2, and then phenyl, carbocation will come here. Carbocation will come here. Okay. Now question is, will there be any further movement? Yes, there is a further movement also, by the way. Why, you know? Now this time again 1,2 hydrate shift will take place from this end. From here, hydrate shift will happen. What is the reason for doing that? See, as soon as the hydrate shift takes place, you will get a carbon, methyl with hydrogen, and now this will get CH plus and benzene. Have you noticed benzene can offer resonance towards this positive charge? That's why the rearrangement can happen towards this side. Okay, so always follow the hierarchy or follow the migrating aptitude everybody. So first thing is hydrogen, then phenyl with donating group, only phenyl, phenyl with withdrawing, 3 degree, 2 degree, 1 degree, and methyl group. Okay, have you all made a note of it? Please do check. Next one, if you notice, we have a phenyl with a methyl group on it, which is electron donating group. Phenyl with a withdrawing group, NO2 is withdrawing group. So definitely the phenyl with electron donating group will migrate. So this is the migration that take place. Positive charge will come here. So this is the final one. Okay. Now the rearrangement sometimes is also observed such a way that a ring is getting expanded. Typically, ring expansion happens from 3 to 4, 4 to 5, and 5 to 6. 6 to 7 in rare cases. Okay. There are certain cases where ring compression can also take place. That means we will notice that instead of ring expansion, compression can also take place, correct? Where you will have 4 to 3, 7 to 6, and 6 to 5. 6 to 5 is very rare. 4 to 3 and 7 to 6 is observed commonly. Okay. Now, notice this case properly and try to understand the positions, correctly where exactly the migration is happening. See, 1, 2. These are two carbons away from the cyclic structure. And now the positive charge is here. The first thing is hydride shift from here to here because originally alpha hydrogens are 2. If the positive charge moves on to the second position, now the alpha hydrogens are 4. So this migration is definitely expected. Thereafter, once you get onto the carbon which is directly connected to the uh, cyclic structure, now the bond breaking will take place. As the bond will break here, this carbon will catch hold of negative charge. This carbon will catch hold of positive charge. From the negative charge, it will migrate towards this first position, hence increasing the ring chain to 6. Now this will be the ring chain. So it will become 6. Along with that, the positive charge has now come over the 6th position. And from the 6th position, again there will be movement of electron. Okay. Because now if you notice the alpha hydrogens, we have here you can see 2 here, 1 here, total 3. Okay. But if you make a hydride shift, 1 to hydride shift here, positive charge can go onto this position. Okay. And now therefore the alpha hydrogens, if you notice, okay. So how many we have? 7. So alpha hydrogens are 7. So this is what you would get. All good, everybody? Right. Notice the next expansion here. Okay. I think this is the same thing which I just explained you. Check out this case now. Expansion takes place from 3 to 4, 4 to 5, and 5 to 6 case, how it is been done. See here, the positive charge on is on this position. Left side, I have a 5-member ring. Right side, I have a 4-member ring. You should always try to open the one which has more strain. And you know that four-membered ring has more strain than five-membered ring. So try to open that first. So between 2 to 5, you break the bond. Make 5 to get the negative charge and 2 to get the positive charge. So from fifth position, you connect onto the first position. Now positive charge will be, appearing on second position. You will see a five-membered ring forming. And here, if you compare the number of alpha hydrogens, you will see right side I have two, left side I have one, total three. Which means on the first position, if at all hydride shift is been done, I will get positive charge here. Now, if you notice alpha hydrogens being, you have 2, 2 and 1. So total 5. So definitely there is an improvement in alpha hydrogen. So hydride shift is possible. And once you get a hydride shift, break the bond here, pushing this carbon as negative charge, and that negative charge will connect here. So making the ring size now, if you notice, 1, 2, 3, 4, 5, 6. So this is the six-membered ring what you get. So this is 1, 2, 3, 4, 5, and 6. And notice carefully, now the positive charge again erupted on second position, appeared on the second position. And you see the number of alpha hydrogens are 3. Again, hydride shift can take place from one position. So now the alpha hydrogens being how many? 4 plus 1, 5. So this shifting is possible. When the positive charge comes at this position, again for the right hand side, the ring expansion is possible again. So this bond will break. From here, the attachment will take place. So you can see it is 1, 2, 3, 4, 5, 6. So here you will have 1, 2, 3, 4, 5, 6. So you can see ring expansion has taken place from here to here, and five-membered ring has converted into a six-membered ring. And finally, after this, there is no further expansion that is taking place. 6 to 7 is a very rare case that happens in a very different case. I'll explain that. But in a regular carbocation cases, expansion, up to 6 is normally observed. Everybody, please do check if you have understood the ring expansion or not. We can discuss. Notice this last case. Suppose positive charge is here. The number of alpha hydrogens are 2. Definitely we can expect a hydride shift. So from here, hydrogen will shift, pushing that 1 degree to 2 degree carbocation. Alpha hydrogens now are 4. So from 4, again a hydride shift can take place. Positive charge can come at this position. So now the alpha hydrogens are being 6. Okay, alpha hydrogens are being 6. So you can see 3, 2, and 1, 6. Now, can this positive charge can move here or not to the next? I mean, the next hydride shift is possible or not? By chance, imagine if there is a possibility, alpha hydrogens are only 4. So it is not possible unless some resonance is helping it out. For example, if I put a double bond here, now let me carry that double bond here. I have a double bond here, double bond here, and double bond here. Now, when I have a double bond, definitely this time the possibility is observed, isn't it? This time, definitely you will have this possibility. Reason is simple, because if you have a double bond, now it has developed a resonance. So you will not worry about how many alpha hydrogens do we have. And now you can see the ring expansion is further possible. So at a four-membered ring, now the bond breaking can take place from here. It can attach here. So what would happen? Here we can have a ring expansion like this. And on this position, I will get a five-membered ring, which was originally four-membered. Now it has become five-membered. If I put the numbering 1, 2, 3, 4, 5. Okay. So this is basically 1, 2, 3, 4, 5. This is the fifth position where you can get. Okay. So where is a positive charge that can come? It can push over the positive charge here, double bond can stay here. Okay, double bond can stay here. So this is the way you can have a carbocation forming. Now you might say, sir, the resonance is lost. Well, what happens if positive charge is coming on the cyclic structure? The pi bond can, attack aerially also. That means from here, pi bond can support onto the second position as well. Okay. So this is still a possibility observed. Got it? So ring expansion can take place from here till this part. After this, I cannot move that positive charge to any new position. Okay. Aerially, this pi bond can only support it without any rearrangement. So that is where you will stop it. Okay. So you will come across many carbocation cases as you go towards the mechanisms, as you go towards various chapters, you will come across that. So here it is just an introductory idea that there is a rearrangement possible. Okay. Now let's dig into further uh, a theory which is about the next intermediates, carb anions. So carb anions, which means carbon carrying a negative charge, if only all single bonds are present, you would say carbon is sp3 hybridized with a pyramidal structure. And if carbon has, one pi bond already existing, then it is sp2 hybridized and it is planar. If it has two pi bonds already existing, then it is sp hybridized and linear. These are the type of carb anions you will generally observe. Now stability. See, in simple sense, if you have a negative charge on a carbon, anything which is donating, electron donating group, okay, destabilizes. Destabilizes. So which are electron donating group effects like hyperconjugation, like, sorry, here hyperconjugation is not possible because it is negative charge. Plus I effect or plus M effect. Anything which is trying to give plus I or plus M will always destabilize. While if you have any electron withdrawing group with on carb anion, so this will stabilize the group. So if it stabilizes, that means it will start gaining more, stability because of the negative charge it has. So now notice this methyl. On methyl, there are only three hydrogens present with a negative charge. So there is no electron donating, no withdrawing group. Now I have one methyl here, one extra CH3. So this CH3 will create a plus I effect. So that will destabilize it. So more the CH3 group, more destability that will take place. So carb anion stability thereby is better for methyl, then ethyl, isopropyl, then tert propyl carbanion, tert butyl carbanion. Okay, so this is the order. Next one, if you compare CH3 minus and then you have an allyl form, allyl will have resonance stabilization also. Then you have benzyl form. Now this time you need to check out based on the resonance. Based on resonance, benzyl has more resonating structures, right, and more stability. And allyl will have relatively better and methyl will have least. So therefore, this will be the order of stability for carbanions in this case. Okay, next. If you compare the carbon, here it is sp3, here it is sp2, here it is sp. So sp can hold because sp has, if you compare the electron negativity wise, sp will have more than sp2 than sp3. And you know that more the electronegativity, carbanion stability increases as the electronegativity factor increases, or this can also be attributed to percentage S character. So you can see percentage S character is more here, so which means that this is the order of carbanion stability. Okay, and the next fourth one, if you compare here on the fifth, 5-membered ring, 4-membered ring, and 3-membered ring, you are seeing carbanion character. You know that if you have to keep this pi bond at around 72 degrees here, correct? sorry, 105 degrees here and 90 degrees here and 60 degrees here. So it has to push a lot of P character here. So the outward bond would have more S character. So here it will have S character. Here it will have more S character. Here it will have highest S character. And you know that higher the S character, more is the stability. So that's why three-membered carb anions are more stable. So you can notice percentage S character in exo bonds. Exo means outward bonds. Outward bonds like this H plus. This outward bond, only when you remove H plus, you'll get a carb anion. So they are relatively easy to break. Okay. Next. See the fifth one. Here there is no resonance. Here there is some resonance. Here there is resonance with aromaticity. So aromaticity will definitely complement it to be highly stable. Okay. Next, sixth one, CF3 minus and CCl3 minus. See, in CCl3, if it comes to carbon, carbon is holding a lone pair of electrons here, like this, with a negative charge on it. And it is being connected to chlorides here. So chlorine has an empty orbital. All chlorides have their own empty orbitals here, where this pi bond can get delocalized like this. It can get delocalized. And that brings more stability to the carbanion. So which one is more stable? CCl3 minus. But in case if you have CF3 CH2 minus, here there is no resonance, here there is no back bonding. So CF3 is genuinely more withdrawing via minus I as compared to CCl3. So therefore CF3 CH2 minus is more stable. Next, if you have one phenyl ring, two phenyl ring, and three phenyl rings, so that means three phenyl will have more resonance stability. Next, if you have NO2, CHO, cyanide, and COOVT, all of them are withdrawing, all of them will stabilize the carbanion. The most stability will be for NO2 because NO2 is the most withdrawing, then aldehyde, then cyanide, then ethyl. This is the order you need to learn. Okay, next. Back bonding wise, if you have a negative charge here, sulfur possesses an empty d orbital where these electrons can be delocalized. So this is due to the back bonding. You will see this one is more stable than oxygen part. Next, if you have a carb anion here, it genuinely has a resonance stabilization on this side, and the same can happen on this side here on two sides here. Now here, this side it is happening thoroughly, but this side it will be weaker now. This side the resonance will be weaker. Reason being, this oxygen's lone pair itself is participating in the resonance here. So which means the most amount of stability will be for B because it has resonance happening from both directions. Here also it is the same, but yet because of this O80, this pushing of electrons is weaker. So which makes it B more stable than C than A. Please check if you have understood this case. Thanks. Check out the 12th one. Here I have a negative charge which makes this ring aromatic. Here this negative charge, this ring is aromatic. Along with that, positive negative charge is there which will attract it. Here you have aromatic ring. Along with that, that negative charge can also make a back bonding towards the empty orbitals of phosphorus. Here nitrogen does not have that privilege. Only phosphorus has empty d orbital in this case. Therefore, which one will be more stable here? In this case, this is how the stability varies. Next, the carb anion will always try to push the electrons towards benzene. Okay, let me show you how the resonance usually appears to be. So suppose if you have a carb anion here, which is CH2 minus, and I have a double bond here. So this minus will be pushed here and this pi bond will be pushed outward. And that brings it minus here, double bond CH2, double bond and double bond. And now if you notice, this negative charge will be pushed here, the pi bond will be pushing outwards this way. And this negative charge will be pushing here, pi bond will be moving on to this side. So if you observe the pattern here, so it is making the rounds around ortho and para position only. So the negative charge will keep moving across ortho and para position. So at this ortho and para position, where the negative charge is appearing, if you get any withdrawing group, electron withdrawing group, it will stabilize. But if you are getting OCH3, which is donating by resonance, then it is destabilizing. So now check out what are the offers that, what are the effects that is being offered onto this group. Imagine if OCH3 is present on the ortho position. At ortho position, it can give resonance energy, yes, because you can see negative charge is coming at ortho and para positions only, and at those positions only, uh, we can see resonance happening. Next, meta. On meta, you should never search for resonance. Para, you have resonance. Next, minus I. OCH3 is much closer to the carb anion at ortho position. Here, at this ortho position, at this side, ortho position. So, ortho positions are much closer here. So, therefore, the minus I factor will be more for ortho, then less and least for para. Putting that into perspective here, definitely resonance is a dominant factor. So ortho will be more stable because it has high, I mean, definitely resono and also high minus I. And after ortho, we have para, then we have meta. Okay. Now let's see the same thing, similar logic from NO2. If you have NO2 at ortho, meta, and para position here, so what do we get? Negative charge always appears in ortho and para position only. So yes, resonance is observed and ortho and para, meta no resonance. At minus I, it is strongly withdrawing group. Meta is at meta, it is only minus I and it is moderately withdrawing. And at para, it is weakly withdrawing. So that makes which is most withdrawing here. The most withdrawing case is ortho, then para, then meta. Okay. Sorry, the last case I have written it a little wrong. Please check. It is donating. Overall, what is it happening? See, you know that resonance energy in this case, which is plus m, is dominant over minus I. Here also plus m, dominant over minus I, which makes this as electron donating group. And here also it is electron donating group. And here it is electron withdrawing group. Here it is electron withdrawing group. So I can say meta is the most stable. Then hydrogen. Hydrogen means regular structure like this. This is a regular structure which is hydrogen. Then comes ortho and para. In case of ortho, at least we have some amount of minus I, and that minus I is greater than that of para. So what do we have? We have this as ortho and then para. Next. And in this case, the last one will be hydrogen because it does not have any effects. Everybody, I hope you understood how to analyze resonance energy, minus I, and everything. See the next one, halogens. In case of halogens, see, any halogen, you can take chloride, bromide, iodide, fluoride, anything. If that is present at ortho, para, and meta position, so resonance is only observed at ortho and para position. Meta position, no resonance. Minus I effect, halogens impart very high minus I effect, slightly moderate and meta, and least at para. Okay, this is minus I effect. And you know that overall, because minus I is very dominant over resonance energy when it comes to halogens, so, and ortho is much closer distance to CH2 minus. Hence, we can say ortho is, ortho is better than para, is better than meta, better than hydrogen. This is the order. Everyone, these cases are clear? Right. See the next case. If you compare the stability of A, B, and C in this case, okay, here we have a 3-membered ring, 4-membered ring, 5-membered ring. But have you noticed something? Whether it is 3, 4, or 5-membered ring, within the ring there is only one pi bond. And this one pi bond can keep moving across the positions here. So this pi bond can be here. As the resonance will push here, that pi bond can become negative charge here. Then negative charge can push here. This oxygen becomes negative charge. Which means the pi bond is moving across all three structures, all three carbons. That means it is an aromatic compound. Naturally, this is also aromatic. This is also aromatic. So all three are aromatic, but here the resonance is more because the pi bond will keep moving at 5 different positions. So therefore, what should be the stability? C is greater than B is greater than A. This is based on most number of aromatic resonating structures. Okay, that is the reason. Next, you have two nitro groups, you have two cyanide groups, one nitro here, one cyano here. And you will see, if at all I write this as A, B, C, D, A, B, C, and D. In such kind of comparison, always give high priority to resonance. By resonance, this because resonance only operates at para and ortho position. Here resonance is observed, here resonance is observed. No resonance here, no resonance here. And since the resonance is weaker in this case, so we can say that between A and B, definitely A is more. And between C and D, definitely we can say C is more. Okay. Now, if you have to compare A, B, C, D, of course, that also can be compared. That is, C is greater than D, and then A is greater than B. This is the order you can get. Okay. Next, in case if you have 3 NO2 groups, just adjacent to each other, and then I have two NO2 groups, and instead of this nitro, I have cyanide. Okay. Now, generally, if you compare the minus M effect, nitro is much stronger than cyanide. You know that, right? Minus M effect of NO2 is stronger than cyanide. And not just that, minus A effect of NO2 is also stronger than cyanide. So in both cases, you will observe that cyanide, nitro should be stronger withdrawing. But see the problem now. Okay. We expect at para position, we should have, resonance happening. So how does the resonance will take place? We expect that the double bond will come here, this double bond here like this. And then the double bond will come here with O minus and O minus. This is the typical way of thinking, right? So that is double bond forming here, double bond forming here. This is the kind of structure we should get. Now see the problem here is, as it is NO2, NO2, NO2 are very close to each other. They are adjacent to each other. Because they are very close to each other, their electronic clouds will repel each other. And this is what we call it as van der Waal repulsions. Between these two, repulsion will take place. Now the problem what happens is, imagine like this, we have two NO2 groups, one more NO2 group here, and at the center there is one more NO2. Now, because they are very close by each other, to avoid that repulsion, this NO2 will completely come out of the plane. Okay, which means benzene ring is like this, and NO2, which is supposed to be planar, now that planarity is lost, and that middle NO2 will turn around like this. Instead of staying this way, it will turn around like this. Okay, so because of which now this NO2, the orbital is perpendicular to that of this orbital. So here resonance will not take place anymore. So due to SIR effect, the resonance is not happening on the central nitrogen. Okay. So here we can say no, sorry. Here we can say no such resonance observed. Okay. So this type of formation is incorrect. Hence, we can say you have to now only compare the minus I effect. And you know that NO2 and CN, minus I effect is more for NO2. But have you noticed cyanide is linear, that does not have any SIR effect like this. So here cyanide is showing both minus M and minus I, while here in this position NO2 is only showing minus I. Okay, NO2 is only showing minus I effect. Now is good. So if at all I have a compound here as 1 and here as 2, I can say stability of 2 is greater than 1 in this case. This is due to SIR effect. Now, if you put all these carbanion cases together, you will notice that aromatic compounds will have the highest stability. Then comparison to that of then you have to compare the hybridization. Hybridization with sp carbon, so which is triple bonded carbon. Then we have resonance stabilization. Then sp2 carbons. Then cyclic structure 1 degree, 2 degree, and 3 degree. So you can see this is aromatic. Next, we have triple bonded carbon. Next, triphenyl, biphenyl, only benzyl, then allyl, then vinyl. You can see next comes vinyl, right? Then cyclo, pentenyl, so propenyl, and then comes methyl carbocation, carbanion, then ethyl, then isopropyl, and 3 degree carbanion. So this is the total order, overall stability order. Okay. So I suppose all of you got that. Right. Now, what is the fate of the carb anions? What would happen to the carb anions? Okay. See, carb anion, if we compare, let's say, I will take this case here, carb anion like this. And carb anions generally take the proton and try to become stabilized. So that means they'll act as Lewis base, extract the proton in this way, and that will bring some stability. Okay. Or it can act like a nucleophile, right? So that is CH3 minus is there. CH3 minus plus, suppose if you have CH3, CH2, Cl is happening. This is how the attack take place, and you will see CH3, CH2, CH3 is forming, and Cl minus has been released out. So this is what I meant acting as a nucleophile. Okay, so these are the two main ways by which carb anions can suppress themselves. One as a Lewis base, the other one as a nucleophile. See the next intermediate. The next intermediate we need to we need to go through is free radicals. See, free radical is a neutral form which is trivalent carbon with unpaired electron. So something like CH3 dot, C2H5 dot, these are all neutral. Okay. These are all neutral, but their octet completion is not done. It has one single electron to be fulfilled yet. Such cases are called free radicals. So usually if an orbital contains a single electron present, that means that atom is showcasing free radical nature. And that will carry an hybridization of sp2 here. So which means this hydrogens and this hydrogens will remain planar. Okay. And see now what would happen. You have sp2 which is planar going towards cf3 which is completely tetrahedral. Okay. That means more the halogens will start increasing, it will start converting more into pyramidal shape. So this is how the shape would look like. Carbon having an hybridized orbital dot, and then we will have three fluorides here. So that will become pyramidal state. So you can see that it will showcase sp3 in this case. It can also show sp3 in this case because it is extremely restricted. Sorry, it is extremely restricted with the bond angle 60. And here also it is sp3 carbon, right? Now see, the above logic is not accurate for, trichlorocarbene, tribromocarbene, carbon radical, and so on. Why? See, if we compare here, as more number of fluorines increases, more withdrawing power increases. So to sustain that high withdrawing power, this carbon has to be hybridized. So instead of staying unhybridized, this CF3 dot will have hybridized carbons. So you'll have sp3, sp2 going all the way towards sp3. Okay. And next, triphenyl carb and carbon radical is sp2 hybridized, but it will have a propeller shape. But it will show a propeller shape. While CH3, CH double bond, CH dot, right? Here it is sp carbon here. So since it is sp carbon, you know, this is less stable. Everyone got a gist about what happens to the radicals here. Now, notice, how do we generate? Radicals are typically generated by breaking the bond evenly, which means you are trying to break the bond so that we can get a homolytic fission. For example, if I take chlorine on with respect to light or heat, it will convert into two chlorine radicals. Likewise, if you have this peroxy benzoate, this is peroxybenzoate, then on heating, the bond between O and O will break. You will get 2 moles of uh, benzoate radical. And here, this side also, it will start breaking, one side on the R, the other side on the N. And the dot on N and N will convert into N2 gas, and these two will remain 2R dash. Okay. So this is how you generate the free radicals. Okay. So whenever there is a radical formation, it will always go through a chain of mechanism, and it's a very standard mechanism for all the for all the radicals. The first step is called initiation. For example, I have a molecule like Cl2 that will initiate the reaction. That is, in the presence of H nu, it will become 2Cl dot. So that means we have done an initiation. After the initiation step, then we have a propagation step. That means this Cl dot will react with something like methane, CH4 plus CH4, neutral form. So first it will become CH3 dot and HCl. So here this Cl dot and H dot will convert into HCl, and this carbon will convert into CH3 dot. And then we have CH3 dot plus HCl. So that will make it see, in such case we can have this as uh, if CH3, sorry, here I need to make this as CH3 radical. So this CH3 radical will again react with Cl2, convert into CH3Cl plus Cl dot. So that Cl dot will again keep on propagating further. This is called propagation steps. Next one is termination step. Termination step is where you have radicals connecting with each other, trying to terminate and convert into a stable molecule like this. Cl dot plus CH3 dot. This usually take place when you have less amount of quantity here. Next, CH3 dot plus CH3 dot. So it will become C2H6. So this is the typical initiation, propagation, and termination steps, everybody. Okay. One such case you will always come across is Kolb's electrolysis. Okay. Kolb's electrolysis, very important in the upcoming topics. So here, if you hydrolyze a carboxylate salt, at the anode end, you will see RCOO minus. It will start becoming R C double bond O dot plus one electron. So that means this electron has been lost and that minus has become a dot here. And thereafter I'll get this as C double bond O dot, and that will decompose itself to become R dot and CO2. And then CO2, this R dot, if at all I have 2 moles of it, so 2 R dot, that will convert into R and R. Okay. This is how the propagation is been done, then the termination has been done. All good, everybody? What is Kolb's electrolysis? If you ask, sir, what happened with the cathode, see, some in upcoming chapters, this is question as well. What is the reaction at cathode? At cathode, we have only water. So water will consume these electrons. So we will get this as OH minus here plus H2. So this is the anode and cathode reaction in Kolb's electrolysis, everybody. Next, what is the stability of radical? See.
Sir.
Yes, beta.
1 second.
Yeah, please make a note. If it comes to stability of free radicals, it mainly depends upon what is the bond dissociation energy of carbon-hydrogen bond. Now, if the bond is weaker, that means it is generating more stable radicals. So, stability is always inversely proportional to the bond dissociation energy. Now, these are the genuine values which you will usually observe. For example, I have allyl hydrogen here. So, as you break carbon-hydrogen bond, you'll get dot and dot. So for that breaking, the amount of energy required is 361. While on this case, if you notice, it will become 364. Likewise, it will start increasing towards this side. So CF3 dot is extremely difficult to be made. Okay. Now you will see some pattern that the radical stability is very similar to carbocation stability, except in few cases. See, first case, you can see 3 degree greater than 2 degree, 1 degree, and methyl. This is the same thing we learned in carbocation. Okay, next. What we learned is exactly reverse when it comes to carbocation order of these three. That is, 3-degree carbocation is observed to be slightly more stable than benzyl and then allyl. Okay. And now, only if you reverse, when it comes to radicals, if you have to, we have to reverse that order. So allyl will be more stable than benzyl, then 3-degree. Okay. So everybody, please do remember the stability of these three. It's important because it is exactly the opposite way of carbocations. Next one, as per carbocation, 2-degree, 1-degree, methyl, vinyl, phenyl, that order is very similar. Next, you have 3-degree, 2-degree, 1-degree, always it is, same as carbocations, highly stable. Okay. Notice a weird act of trityl radical. Trityl radical is having three phenyl groups on it. Okay. See, when two trityl radicals approach each other, correct? So this C dot will connect onto uh, bond here. Okay. So that means it will break carbon hydrogen bond and eat away that H dot. Okay. So what is this? What is that form you can get? You will get this as benzene with carbon and having two phenyl groups here. And then here, as soon as the dot starts falling here, uh, the pi bond will suddenly start shifting onto the other side. And that gives you a momentum of pi bonds here like this. Like this is the genuine. Please check. Next, what is the fifth one? As a carbocation, you'll always view alpha hydrogens, but as a radical mechanism or radical intermediate, you'll only look into the type of structure. If it is cyclic, generally more dominant than open chain. So although both will have same number of alpha hydrogens, it should be always cyclic more stable than straight chain. Next, here if you notice, this is very similar to that of carbocation. Suppose if you have an OCC here, you know that OCC is more stable than any form. Very similar to that, we have H double bond O dot, which is similar to that of, which is greater than that of benzyl radical. Okay. Now, please read these lines carefully, everybody. See, radicals are stabilized by plus R and minus R when they are attached to free radicals. This attributes to resonance and called caprodative effect or push and pull effect. That is, if you have this case here, you can push this pi bond here, make it into octet completion. But the problem here is this oxygen still has not completed the octet. Okay. So this is the way it will be observed. I mean, these two are the resonating structures. And because of that reason, you will see this compound has observed to be more stable than benzyl radical. And next, if you compare this one, amides, these two amides, the dot on oxygen represents it is more electronegative. Okay. Now, therefore, if you come across this part here, just like how we did it for carbocation, I mean, how we did it earlier in this case, right? Sorry, in this case here, very similar to that. If you have CH3C double bond or CH2 dot, that will be same as this one. Okay. Now, if it comes to these two comparison, definitely you will see CH2 dot that will be slightly more stable than CH3 dot here. While here definitely it is the case where octet kind of case is completed here. Here it is not happening. So these are few examples you need to learn that how the radical stability is. Now, what is the fate of radicals, everybody? What would happen to the radicals here? See, radicals more often try to terminate themselves. That is, R dot plus R dot will convert into R and R form. Okay, next. It can always generate another radical as well, which means if at all you have R dot plus Br2. So what do we have here is RBr plus Br dot. Similarly, in case if at all it can disproportionate, that is CH3 CH2 dot, right? Next CH3, I have CH2 dot. Now you will notice that here at this position where you have three hydrogens, let us put this as two hydrogens here. So CH2 and then we have H. Now this would start breaking into pieces like this. So we'll get this as CH2 dot, and that CH2 dot here and H dot here, that will convert into, that will convert into CH3 CH3 plus CH2 double bond CH2. That's it. This is one is getting reduced, the other one is getting oxidized. Done. Next, radicals are often observed to get added onto C double bond C as well. Okay, so which means if you have CH2 double bond CH2, right, and that when you react with something as Br dot, in that case we will get this as CH2 dot. This is how the addition can take place. Please do check. Done. Let's go to the next one. Carbene intermediate. Carbene is also a neutral bivalent species with only 6 electrons present in it. There are two types of carbenes. One is called singlet type, the other one is called triplet type. In singlet type, the hybridization of carbon is sp2, where it has a complete empty orbital, and then it has three orbitals, and all three are hybridized orbitals. Because of that hybridization only, it is showing sp2. Okay. The bond angle between these two hydrogens comes around 105 degrees. Okay. Next. See, in the singlet form, if you compare, why you use the word singlet, this comes with that uh, formula which is Hund's spin multiplicity. Okay, Hund's spin multiplicity. So what does that mean? The spin multiplicity is always equal to 2s plus 1. 2s plus 1. Okay, what is this s? S is the total spin. Sorry. Total spin. Total spin of electrons. So, for example, let me show you. If you have let's say 3 unpaired electrons. So then the total spin will be equal to 3 times of half. Hence the formula. So total spin will be equal to half into number of unpaired electrons. So in case of CH2 singlet, there are no unpaired electrons. Since there are no unpaired electrons, so S will be equal to 0. So S is 0. So spin multiplicity is equal to 1. Since you are getting 1, that's the word used, singlet carbene. Now, if you apply the same Hunt's rule for triplet form, CH2 can also exist in a triplet form. Here, both the orbitals will get 1 electron each. And the bond angle now swept is 135, hybridization is sp. Okay. So now if you notice the spin multiplicity, 2s plus 1. So s being 2 times into half, which is 1. So if it is 1, then spin multiplicity, which is equal to 2s plus 1, is equal to 2 into 1 plus 1. Okay, so that comes out to be 3. Because it is 3, that's the reason why we use the word triplet. Because the spin multiplicity is coming out as 3. General stability, if you compare between these two, triplet is always more stable than singlet, generally. But if it is compared with a dichlorocarbene, like there are two chlorines here, two bromines or two iodides here. In that case, what would happen here is one of the orbital will be left empty, and this chlorines would start making back bonding with this empty orbital. And to encourage that back bonding only, they will remain as singlet form. Instead of triplet form, they'll try to remain as more singlet forms. Okay. So let me write down the reason. The reason for that is back bonding. See, back bonding is possible in singlet form. Next, so if we compare the overall stability here, we will see CF2 CCl2 greater than, right? So this is the order of stability, and all of these are in which form? They all are in triplet form. Sorry, they all are in singlet form here. Done. Now, how do we usually generate these carbenes? See, first case, how we can get is by alpha elimination. Alpha elimination, best example is like this. I have CCl3 and H. This is chloroform. And remember, chloroform, when you react with a strong base, ETO minus, so it will become ETOH plus ETOH plus CCl3 minus. Okay. Now notice this CCl3 minus, what you get here is a challenging. So CH3 minus, CH3 minus, this is the anion form. So it will, as soon as this C2 have three chlorides are highly unstable. It will start becoming CCl2 minus plus Cl minus. You can check out why it is unstable. See, lone pair is here, and then we have three chlorine groups. So now you'll notice that these three chlorides are pretty much very close to each other. And that's why there is a relatively strong repulsion between them. To avoid that repulsion, one of the chlorine will come out, creating CCl2, CCl2 only, no minus charge. So now you notice that it has an empty orbital with a lone pair. So this is called dichlorocarbene radical. So this is called alpha elimination. Because why alpha elimination? You will notice that hydrogen as well as chlorine, both of them are going from the same position. That's why it is called alpha elimination. Another way to generate the carbene is from photolysis. Photolysis or pyrolysis of dizo alkanes. That is, if you have R, CH, N, triple bond N with plus and minus, these kind of forms are called dizoalkanes. Now, this on heating, and this on heating will give you RCH dot here plus N2, right? Next, the same structure could be like this also. CH, sorry, we'll do one thing. CH like this. N, another N here with a double bond on it. And here, how the bond breaking take place, this side will get dot, this side will get dot, this side will get, this side will get. And that's how you'll get this as RCH, RCH, an empty orbital with and one lone pair plus N2 gas. So this is the carbon which you will get. This is called izide, and izide is getting a carbene intermediate. Now see, what is the fate of carbene here? Okay, first thing is dimerization. Okay, so which means if you have R, CH, you know, I have a pair of electrons, one empty orbital. So that if I take 2 moles of it, so if at all we take these 2 moles here, okay, they will try to dimerize with each other. So that means you will get this as R, CH, double bond, CHR, yeah, this way, okay. This is the case of dimerization, okay. Next, addition to the pi bond here. That is, if you have CH2 double bond CH2 plus CH2, one pair of electrons and one empty or vacant orbital. Usually what happens is wherever there is a pi bond, the CH2 will instantly go and connect here. So we have this as a double bond here, and then comes CH2 like this. So basically it is getting inserted. Okay, and now this double bond will not be there. Sorry, now the double bond will not be there. So it will be like this. So what are we getting? You're getting an insertion of this CH2 between the pi bonds. Now instead of this hydrogen, let us put this as a dichloride. So 2 chlorides here. So in that case, this is how it will get connected with 2 chlorines on the blue, on the exo bonds here. What if you have triple bond? So no problem. Triple bond, we take 2 moles CCl3 empty orbital. Now if you notice here, we will get one methyl added up, one methyl added down. So this is the product you will get. Right? Please make a note, everybody. See the next intermediate. The next intermediate is benzene. See, benzene is basically a benzene with one pi bond outside the benzene. How is it located? First, all the carbons in this benzene form are sp2 hybridized only, including these two. These two are also sp2 hybridized. There is a 6 pi electron cloud inside the benzene ring, which makes it aromatic. And you see 1, 2, 3. All these pi bonds, 3 p pi bonds are present. All three are p pi bonds. And there is one pi bond here between these two carbons, which is sp2 and sp2 pi bond. So sp2 and sp2 combined pi bond. Okay. So this is only one of those instances where a hybridized orbital is making a pi bond. Otherwise, a pi bond is always between the pure orbitals. But here you notice that it is between two hybridized orbitals. Remember, it's an intermediate, so its lifetime is extremely low. It'll disappear in fraction of seconds. But we need to understand even in that fraction of second whether there is some stability established or not. Now, for this benzene, there are two resonating structures we can make. One is in this side, one is in the opposite side, two Kekulé structures. So obviously in the one bond, we can see the triple bond more likely happening. Here the triple bond is not observed much, so therefore stability wise, 1 is greater than 2. This is about benzene. How do we generate? Generally, benzenes are made like this, where you would have a regular benzene having some withdrawing group like chlorine. Adjacent to that, we must have a hydrogen. In that case, NH2 minus being a very strong base, it can extract this H plus and then push this sigma electrons and then removing out the chlorine part. So what do we have? Here we have a double bond, and now triple bond. That's how we can get the benzene form. Next, electrolysis of phthalates. Phthalates can also give you the same thing. That is, in case if you have phthalates is COO minus, CO minus like this. Imagine making, KE, that is Kolb's electrolysis. When you make Kolb's electrolysis, just now I told you in Kolb's electrolysis, wherever there is a COO minus, that will become COO dot because it will give away electrons. And this on heating will give away carbon dioxide. So what do we get? So here we have a double bond and triple bond is outward plus 2 moles of CO2. That's how you will get benzene. Okay. These are most typical ways by which you can get the benzene form. Okay. And let's see what is the fate of benzene. Usually, benzenes will interconnect with each other quickly. That is dimerization or trimerization part. If the benzene concentration is low, it will end up dimerizing only. So if it is dimerizes, we will going to get like this way, this way. Okay. So ring and ring. So what are we getting? biphenylene. So we will get biphenylene as the product. If only I have high concentration this time, that means if you have more number of intermediates, it will start making, much better ring in that case. That is, I will have a six-membered ring connected like this. So, which automatically makes the central ring also aromatic. Okay, this is triphenylene. All good? Everybody, please do check. Right. So this is how much we need to learn from